In this series of videos, we are understanding object-oriented programming from a philosophy of language perspective, and we are doing that by recreating the famous game Asteroids. So this is the final project of this series. You can see that we have the spaceship moving with shooting and bullets. We have a health bar, we have a spawner of asteroids, we also have spawner for the saucers. Let's see. When the saucers, yeah, we have the saucer there. You can see that there are asteroid fragments, right? And when we die, the ship explodes and we can restart the gameplay session. And in this video, we are going to go from an empty project into the creation of the very spaceship itself. So the movement of the spaceship. We're not going to implement the thruster effect here, but we can do that in a future video. The thing that we are going to do here is the movement of the spaceship and the controls, because this will help us understand some principles of object-oriented programming. So without further ado, let's understand how object-oriented programming works. The major advantage of understanding how object-oriented programming works, especially from the philosophy of language perspective, is that you can think about solutions of the problems with natural language, because when you program, especially using the object-oriented programming paradigm, you are giving meaning to terms and creating your own vocabulary. So you can rely and leverage other people's vocabularies. So this is what a programming library is. Someone else already created their vocabulary, and you can leverage their vocabulary to solve problems that are more complex, or problems that you are trying to solve in your specific context. But you can also create your own vocabulary of solutions or other problems or tools that you can also leverage. And by understanding that, for instance, a class is nothing but the definition of a term in this vocabulary. So let's say we create an object that can simulate physics and has some collisions and has some movement, and it has some drag and etc. It has some properties and it performs some behaviors and procedures. We can give the name of this a name for this object, such as RigidBody. So whenever we think about something that moves simulating physics, we can say, oh, this is a rigid body. So for instance, as we're going to do in this video, when we create a spaceship, we think about a spaceship that should have a physically simulated movement. We can say, oh, a spaceship has a rigid body, because we are combining the definition, the term rigid body, within the term of the spaceship, which is a more complex problem to solve, but it can rely on the definition of the term rigid body, because when we define the problem of the spaceship, which is an object that moves with physically basic simulation movement, we already have this solution solved through the term rigid body. So this is what object-oriented programming allows us to do, to extend definitions and combine them to solve more complex problems and create our own vocabulary to solve problems and think about the solutions in terms of the vocabulary that we are creating. So I'm going to split the screen here so we have some learning material on the screen as well. And let's start from the definition of object-oriented programming that we are going to use throughout this series. So object-oriented programming is a paradigm of a programming language. It doesn't mean that a programming language should use object-oriented programming, but rather than you can approach it from an object-oriented programming perspective. And to define object-oriented programming, we have some major features that a language should provide to us so that we can express our thoughts, because this is what programming is a formalized expression of a thought. And to achieve that, object-oriented programming provides us some features. And in order to a programming language such as GDScript to be considered a object-oriented programming language, it should cover all these features and should provide these features to us. So let's understand what these features are. One of the core aspects, one of the core features that we should be able to do within a object-oriented programming language is the ability to bundle data and procedures together. So data and procedures we saw in the previous video. So data is basically the information that you need to solve a problem, and the procedure is how you are going to work on this data to achieve the solution of this problem. So how this data will change and modify to achieve the solution of the problem that you are trying to solve. And to this bundle, to this set of data and procedures, we give the name of a class. So again, as we are going to see, a class is nothing but the definition of a term. So a class has a name that you can reuse across your project, and when you think about your class, you are going to think about whatever is the meaning it carries. And as we are seeing here, the meaning of this class is its data and its procedure. So this is what I mean by the definition of a term. The term is the class, so you give a name for the class, let's say a RigidBody, and the meaning is the data and the procedures that it carries. So keep that in mind. When you put this definition into context, so when you form a phrase, when you want to form a phrase using this terminology, using the definition of a class, for instance, you create an instance. What is an instance? It's when the abstract solutions take a concrete form. So what I mean by that, let's try to understand this from a metaphor. Let's say that previously, without object-oriented programming, people used to think in terms of data and procedures separately, right? So let's say you want to make the recipe for a cake, for instance, and in one document you had the ingredients for the cake. So let's say eggs, milk, and flour. And on another document, on another completely different document, you had what you should do to make a cake. So you should mix the ingredients, bake it. In object-oriented programming, you bundle these two things into a single thing called cake recipe, right? So the cake recipe has all the ingredients necessary and all the procedures that we work we do with this data to achieve the cake. So this is the definition of a cake, for instance. This could be the definition of a cake recipe. But when we think about the instance, the object, it will be the concrete execution of this data, of this procedure, of this recipe. So it's not the cake itself, the object, the instance is not the cake itself, but rather when you execute the recipe. So when you pick up, like, let's say 3 eggs, 3 milliliters or 300 milliliters of milk, 100 grams of flour, and then you mix everything and you bake it, and you have a cake in return. The cake itself is not the object, but the object is all this context of putting this recipe into context. So executing this recipe, this is what an instance is. And in that sense, an object is a reference to this instance. So let's say we have a recipe A and recipe B. They can generate two different things, but I'm going to refer to recipe B as recipe B and to recipe A as recipe A. So let's say I can make cross-reference even. So I can say, hey, recipe B, ask recipe A if it already finished baking before we can bake recipe B, for instance. This is something very interesting about object-oriented programming, is the ability to make objects communicate mutually. So now that we understand that an instance is a class put into context, so let's say that we have a class meant for creating batter, like the cake dog. Yeah, the batter, when we mix eggs, milk, and flour. So we have the phrase, I need to bake the batter to make a cake. The definition of cake is a baked batter. So we are combining this terminology, and in this term, or in this phrase, I need to make the better. The object here is the better, right? So let's say we can reuse the same definition of better, since we now created the term, we created definition of better. What is a better? It's the mix is when you pick up some eggs, milk and flour and you mix them together, right? So this is, let's say, the better. And when we think about it, we can reuse this term in the following phrase as well. I need to fry the batter, and this will be the recipe for, let's say, a pancake, right? So the pancake here will be another class, and the cake here will be another class, but the object is whatever I'm referring in these phrases. And since this object is put into context and it is being executed and processed, this object can be in any given state. So what is a state? Is a set of values for an object properties. So whatever the set of values an object currently is in, it will be its state. So let's say we have an object, an instance of the class better that is that has 3 eggs, 300 milliliters of milk and 100 grams of flour. When we add a new egg to this batter, let's say we need to make it more eggish. So we add like one egg, an extra egg into this recipe, making it 4 eggs, 300 milliliters of milk and 100 grams of flour. This is another state. So if we add like another 100 grams of flour, making it 200, this will be another state. And if we add if we change anything in this data, it will be another state. And through these changes, usually we do these changes through procedures. So this is why we have data and procedures. When we change these data values, we do a mutation. So keep that in mind, because since we can have an almost infinite number of states in a given instance, in a given object, we can run into many problems because we didn't foresee some states that an object could be in. And in future videos we are going to talk about the state pattern, which will basically limit all the possible states that an object can be in, so we can manage the transitions, the mutations from one state to another. But keep that in mind, a state is the set of values that an object currently has. So when you change these values, when you change the data of an object, you perform a mutation. This is important because we are going to talk about in mutation terms from now on. Well, and how do we perform mutations? We can perform mutations in many ways. It can be very straightforward, very deterministic, so this will always change that way. But it can also be a conditional statement. So conditional statements are structures of code that follows from the if, else, and in case of GDScript also elif, and switch, and in case of GDScript we typically use the match statement instead of switch statements. So based on that, we can branch the logic and say, well, if the application or whatever data that we are checking in accomplish these conditions, the data will change following these instructions here. Otherwise, it will change following these other instructions. Or you can basically just check for if this happens, change the data accordingly, like mutate this data to this value. So if statements are how we branch the logic, making it adapt depending on the context that we are using our solution of the problem, based on the context that the class is put into. And notice that conditional statements, data, and procedures are not exclusive terms of object-oriented programming, right? This is the basic of programming. But classes, instance, states, and mutations. Mutation, you can argue that is a term exclusive to object-oriented programming paradigms. So the paradigm. So we are going to typically refer to the change of values in terms of mutation in the context of object-oriented programming languages. But conditional statements, data, procedures, types are not exclusive. Now we are going to enter in the realm of what is actually provided exclusively by object-oriented programming paradigm, so that we can create our vocabulary using the object-oriented programming paradigm language. So let's talk about inheritance abstraction and polymorphism, encapsulation, and composition as well. So inheritance is perhaps the trademark of object-oriented programming. So what inheritance is that you're going to extend the definition of a class, right? So you have a parent class or a superclass, which is the term that I prefer using, and you're going to inherit or specialize or extend, which is the term that I also prefer using, this class, creating a subtype, a subclass of this superclass. What this will allow you to do is to reuse the superclass code. So you are going to extend all its data and procedures and add more. So you are going to extend it. But I will be an advocate, and I saw this from other developers as well, that you should only use inheritance when you are going to both reuse the superclass code and override it. And we are going to talk about overriding the superclass code when we talk about polymorphism. But under these two circumstances, so not one, not the other, but both, you want to reuse the definition that you created for a class and override it. And there is some advantages in overriding logic, in overriding the superclass code as well. But on the other hand, we have composition. Composition is when you have a class that is going to use another class, so it will be a user class of another class, and it will basically just use the code of this class and combine it with more code. So it can be more code from other classes, or it can be more code from the very class itself. In polymorphism, I am a huge advocate that abstraction is perhaps the most powerful skill that a developer can develop. Because what abstraction will do is to allow you to solve issues without having to think in terms of the implementation details, just like we are doing here. So we have like a recipe for batter, we have the recipe for cake, we have the recipe for pancake, and somehow it bakes, somehow this fries, somehow this implements, like it uses the oven, this one we use pans. This is what we have been doing in this metaphor. We are being abstract. We're not talking in terms about X could be a data type. For instance, we are going in the batter recipe, X is an integer type, and milk is also an integer type, and we're not going into details. We're not talking about in terms of details. We're being very abstract. We're just trying to understand the problem and create an interface to solve it. This way, we could right now create a batter class, a pan class, a pancake class, a cake class, a oven class, and just make the interface, making them communicate using this interface. And this is the most powerful thing, because you're not wasting time into implementation details. You are just creating the interaction between these classes, so that when you create the implementation details, they won't have to mess around with each other's data, because everything will be right up front, be rigged together. And this is why I think that abstraction is perhaps the most powerful skill that a developer can develop. So it's basically just high-level problem solving without implementation details. And polymorphism is the opposite. So you already have everything abstracted. You already have all the data, all the procedures, the contracts. So we are going to talk about contracts in a bit, but all the contracts set, and polymorphism will change or will implement these contracts. So let's say that in order to bake, instead of just saying, oh, you need to, let's say cakes are baked better, right? So the bake procedure is picking up the batter, putting it to like aluminum bowl, and putting it to an oven, turning on the oven to a 280 degrees, waiting for 15 minutes, turning off the oven, picking up the batter, and you'll have the cake ready. So this is the implementation details. But using abstraction, you are just saying, oh, you need to bake the cake, and when you bake the cake, you are going to have a concrete cake object in return. The polymorphism can change that. So let's say we have two types of cakes. Maybe we want a cake that doesn't need to go to the oven, but instead it will bake into, instead of a gas oven, it will bake into an electric oven, right? So the bake contract will basically say bake. But the way that an electric baked cake will implement the baking is using an electric oven, and the way that the classical cake will implement the bake procedure is using a classical a gas oven. And this is how polymorphism works. The same class cake can have two different behaviors, but the interface will be the same. So for outside classes, for user classes, the cake class didn't change if we are working with a electric baked cake. It will stay the same. The logic will be the same as if we were working with a classical baked cake. Finally, one of my favorite tools that we typically use in object-oriented programming languages is encapsulation. So encapsulation is essentially the skill, the technique of providing high-level communication, bundling complex procedures into simpler, intuitive interface. What that means is that instead of allowing user classes to have access to every implementation detail that a class goes through in order to execute whatever purpose, whatever responsibility it has, instead it will basically say, hey, this is the way that you are supposed to use this class. Don't mess around with anything else. And typically what we do here to enforce this encapsulation is to use like private variables, private methods, and other stuff, and basically adding a layer of encapsulation into some stuff. So for instance, in Godot engine in GDScript, we can use setters and getters to hide some procedures that happen when we set a value into a variable or when we get a value from a variable. And well, encapsulation is way simpler than that. It's basically just providing a nice interface for a user class so that it doesn't have to be concerned about implementation details. You basically just create a capsule of some simple components and call it and give it a name. So just like a medicine, right? In a capsule you have like many components inside it, but when you drink it, when you consume it, you just know that it is a capsule, and the doctor will basically instruct you to use this capsule. It will not instruct you to know which each of these of the components that it's inside this capsule. The doctor will basically say, hey, use this medicine right here, this capsule, just drink it with water, basically. And you just have to be concerned about drinking the capsule with water. This is what encapsulation is. You are going to take all this data, all these procedures, and create a nice interface that other objects and other classes can use to interact with the classes with the class that you are creating. And this to me is also one of the coolest skills that you can develop as a object-oriented programming developer, the ability to create nice interface using encapsulation. And finally, before we actually dive into action, because I know that you are looking forward into that, I just want to say that in object-oriented programming, it's better to turn everything into objects whenever possible, so that you stay in control of your vocabulary, because you will know what each type that you are creating, what each word that you are creating in your vocabulary, in your library, will mean and will do. So this gives you a lot of power and control over the logic that you are creating. So for instance, in Godot engine, the Godot engine developers created a class for strings, which are typically a primitive type, but in Godot engine a string is an object type. So this is very cool because it allowed them to implement some cool methods that can work with string types. So for instance, you can format string types, you can search, you can filter, and other stuff like this. So by turning the string primitive type into a string type, a string object, a string class, it allowed them to make more to extend the behaviors of a simple string. And we now also have the string name class as well, which extends the behaviors and the data from the string type. But this is the final advice that I want to share with you. Turn everything into objects. And also this is the base of most object-oriented programming design patterns, is to turn things into other things. So for instance, we have the state pattern, which turns states into objects. We have the command pattern, which turns procedures into objects. We have the strategy pattern, which turns conditional statements into objects, so on and so forth. So turning things into objects is also, I think, that is the most powerful skill that you can develop as an object-oriented programming developer. So that said, let's go into the Spaceship implementation. Well, to start with our project, I'm going to download this start project right here, which is basically an empty project with a sprite inside and some input methods already set. So this sprite is what we are going to use throughout this whole project. So these are the assets that we are going to use. And the image itself is some data that we are going to process in order to achieve the desired outcome that we want in this project. By the way, if you don't have access to this start project and to the finished project, I'm going to put a link in the description so that you can become a Ludonaut. By becoming a Ludonaut, you support my work here, and also you have many benefits such as discounts on my shop. So if you want to acquire my first line to first dollar course, you have 20% discount on that, 20% discount on my first book, on my second book, and you can get access of the files that we are going to use in this very series right here for free. So this is free for all Ludonauts. And also you will also have discount for the Mission XIII membership. So it's a mentorship actually that you can get with 20% discount if you are a Ludonaut. And this is a 6 months long mentorship that will take you from the very basics, so introduction to object-oriented programming, how you can save files, how you can load files, and at the end, by the end of the 6 months, you are going to release your first game. So this is one of the portfolios of my students, Victor, so Lotovic. You can check out his other platforms here, so social medias right here. And we finished together Ornament Tower, which is one of the coolest projects I saw from my students. It's a Sokoben's kind of game, and you can see that in the credits we have right here Henrique Pig Dev Campus, which is me. And after that, Victor actually created many types of projects that are very, very valuable. For instance, Character Controller, which is basically a template for games that has controls similar to Mega Man X and Mega Man X2 and that kind of stuff. So these are the features: input buffer, crouch, acceleration, deceleration, wall jump, wall slide, and other things like letters as well. And recently Victor launched as well the asset pack. So this is basically a state machine controller that will help you create more states and transition between states in Godot engine. So Victor was one of my students. We made a, I think that it was a 6 months long mentorship, in which at the end he finished up Tournament Tower, and after that Victor was empowered with knowledge to create this character controller, and after that and recently this asset pack that is a state machine controller as well. So Victor was one of my students in this mentorship. He is an artist, and after that, after the mentorship, he learned how to create and develop games in Godot engine. So highly recommended to check that as well. And again, if you are a Ludonaut, you have 20% discount even on the monthly game development mentorship, the Mission XIII. So go there, the link will be in the description. But that said, let's download the start project and start implementing the Spaceship movement. So I'm going to start by downloading the start project, and I'm going to save it on my download folder. I'm going to start by extracting it, extract, and I'm going to open it with Godot 4. Let's see if it's already appearing here. Godot 4.4. Yeah, this is the one. So you can see that all that we have here is basically just the sprite sheet that I showed you earlier. And you can see that in the project settings, input map, we already have the thrust, the turn right and the turn left input mapping. So these are directions that we are going to use in the controller. So I already set them to use, so we don't waste time setting them in the future. So based on that, we are going to start by creating the rigid body. So look at how things work in Godot engine, right? They already provide us, so let's change this back. They already provide us with many solutions here that we can rely on. And the way that we can extend these solutions is by using what we need, the base, the core functionality that we want. In this case, a rigid body, because rigid bodies simulate physics, and especially physics movement and collisions. And then we can extend this behavior, which is exactly what we are going to do next. So I'm going to call this Spaceship. Remember, we are creating our vocabulary here. I don't want to call this a rigid body because I don't want to refer as a rigid body in the future. I want to refer it as a spaceship, because the problem that we are trying to solve, and this is where this approach of using philosophy of language will help us understand, is that the problem that we're trying to solve is, I want a spaceship, and this spaceship will move using physics simulation. So this is the definition of this spaceship. I want a spaceship that will be controlled by the player. This is the problem that we want to solve. So the first step is to create this spaceship that move using physics simulation, which is exactly what we are doing here. I'm going to save this, and the way that I like to organize my projects is by breaking things down into something that I can think more clearly. So for instance, a spaceship is not a player yet, but the player will use a spaceship. But a spaceship is an object, so I'm going to put it into the objects folder, and I'm going to create the spaceship folder here. So I'm going to save it, and just so you see the way that I like to organize my project structure, I'm going to remove my camera and show to you. So I have actors. What are actors? Actors are basically objects that have intentionality. They have agency. They act in the game. They have a purpose and they act towards it. So this will be where I will put the player, the enemies, the bosses, and the NPCs as well. So moving back, I also have areas, which are segments of a level that I can combine. I can create these areas, I can work on them, and then I can combine multiple areas to create a level. Talking about levels, I also have levels here, which are basically just a representation of the game world itself, the virtual world that we are dealing with, and it can have the level will be the combination, composition of objects, agents, and actors and areas. This is what typically I will refer to as a level, a bundle of actors, actors, areas, and objects. So moving back here, I also have what I call game, which is some meta structures such as quests, the game system itself, the score system, the progression system, everything that is related to the game itself, the system of incentives that I'm creating, right? Other things here are basically just the package of the game. So I also have the interface. This is kind of like self-explanatory, but these are the interface elements, individual elements that I can again reuse and combine them together. And this doesn't refer only to like the HUD, right? The HUD. So this will be the main menu, but the buttons of the main menu and things like that. Because the main menu is what I call a screen. So a game is composed of many screens. Let me just change that. Screens in plural. A game is composed of many screens. So we have the main screen, the splash screen, the game screen, the pause menu screen, the options screen, the score screen, the high score screen, the achievement screen, the game over screen, the loading screen, the saving screen, so on and so forth. And screens are basically the final thing that compose the game in my perspective. So for instance, the game screen will have the game object, the quest system, the level, that, as I say, the level is composed of the actors, the objects, the areas. So the screen will basically merge the game world, which is the levels, which are the levels, and the interface together. It will mask these three elements, and as you can see, it's kind of like a pyramid, right? We have a lot of objects that work individually, and then we combine them into areas and levels, and then we add interface to them, and then we have the screen, which is the final object, the final scene that I work with. But that said, let's go back to the tutorial. I have here the spaceship. It's already saved on my objects folder, and I'm going to extend this behavior. So this is, as I said, as you the way that you add more behaviors. And again, let's remember this always. You should only use inheritance when you want to reuse code and override code and modify existing code. And this is exactly what we do when we extend a node with GDScript. We have some basic functionality, and we are going to override some methods, especially the ready method, the physics process method, and as we are going to see later on, the input method, virtual methods as well. And we are going to say what will happen when Godot process these methods. So as I said, we have what we call interfaces, right? We have abstract solutions, and the Godot engine engineers, they created a very interesting, this is not, of course, this is not exclusive to Godot engine, but the Godot engine creators made a system where the way that nodes are processed is by a scene tree, and the scene tree will always calls some methods, such as the ready method, the process method, the input method, the physics process method. And as it processes these methods from these nodes, from these classes that we call nodes, it will always process whatever we put inside these methods. And this is how we add some behaviors to our classes to be processed in the scene tree. Everything else will basically not be called unless processed by other objects. But the way that we approach Godot engine is by overriding these virtual methods. So let's see how this works in action here, in practice here. So I'm going to do something here that is called serialization. What is serialization? This sounds a little bit complex. This is going a little bit beyond the scope of this video. But serialization is when you put some data inside a file that you can load in process time, and use this data to set the values, the properties of some objects in real time. And the way that Godot does that by using the export keyword is saving whatever data that we are going to pass here into the scene itself. And scene files will be loaded in process time, and it will take this information instead of whatever we put in the class. So for instance, I'm going to use here linear acceleration, and what we have in linear acceleration is a real number, which is a floating number, as we call in Godot engine, that will add this amount of speed per second square into this object. So linear acceleration is a property that Spaceship or the RigidBody doesn't have by default, but it has the linear velocity. And what we are going to do is to add this amount into this so that the spaceship will move. And the next thing that we are going to add is the angular acceleration that we are going to use to turn to rotate the spaceship around. And this works with radians. So this is the amount of radians per second that we are going to add into the angular velocity here. And I'm also going to add a variable called turn direction that let me explain this to you. So we have what we call an abstraction here. A direction is a vector too. It should be an arrow pointing in a given direction. But since we already have the linear velocity that will always pointing into the direction that the spaceship is moving, this will kind of be like a constant, but it's not a constant, as we are going to see. The turn direction will be just an abstraction. Are you going to the left, or are you turning to the left or to the right? So going back here, I'm going to set it to 0 by default. And finally, I'm going to create the thrust direction, which will be a vector 2. So notice that vector 2 is not a default type from like most programming languages. This is a class created by Godot engine, and this allows them to add some properties and some methods to this class. This is a b-dimensional representation of a vector, which is basically something that has a direction and a length, and we can use this to create movement. So by default, it will be a constant that is inside, is a data type that is inside this vector2 class, that is basically a vector that has a value of 0, as you can see in the description, 0 and 0. What this will mean is that this spaceship will start by not moving in any direction. And the way that we are going to implement all this data, and that we are going to mutate this data, is overriding the physics process. So as we just saw, the way that we implement behaviors in Godot engine is by overriding the virtual method. So this is the reason why we extend the node behavior, because we are going to override the virtual methods here. So we have the physics process, and I forgot to talk about that, but this is what we call a contract. So not only this, but this whole thing here. So a contract is nothing but the what we are providing to other classes through the implementation of this class. So for instance, the contract of the RigidBody implementation of a physics process is a function called physics process that will not return anything, but it will provide a delta. A delta is basically the difference between the process, the time of processment of one frame to another. So it's this difference, and this helps us maintain a consistent flow of increments. So for instance, if it took, we usually multiply delta to make any adjustments that rely on time be consistent. So for instance, if it took 0.1 seconds to process one frame to another, we are going to multiply this delta to make this increment here adjust to this time of processment. And what this will do is that if let's say a player computer is a little bit slower, it will make up for this difference in process time. So this is exactly what we are going to do inside this function here. We are going to take the linear speed, the linear velocity, and we are going to do the following. We are going to mutate it based on a vector2 that is going to point to the right. Why I'm using vector2 right here? Because in Godot engine, let me change back to here. In Godot engine, a vector rotated by 0 degrees will point to the right, because this is the 0, 0 rotation vector. And this is exactly what we want, because if we rotate it, we want to adjust based on this vector pointing to the right, because whatever offset that we rotate here will take in account the default rotation, which is a vector pointing to the right. This will be clearer as we create the script. So let me undo this transformation here. Okay, so a vector2.right rotated by whatever rotation this object is, so whatever the spaceship rotates. So let's say it starts to the right, this is the default rotation, and if we start to turn the spaceship around to maneuver it, it will make up for this rotation in this calculation. So let's say if we start to turn to the left like this, it will pick this vector2 rotated to that's not rotated, pointing to the right, and will rotate it according to the spaceship rotation. This will make so that our acceleration will always be pointing to the spaceship tip, to the tip of the spaceship. And what we are going to do here is that we are not going to set, because this is a set operation, right? We are like this, we are setting the linear velocity to this. We are not, we don't want to do that. We want to increment, and this is the symbol that we use for increments. And we are going to take this vector 2, this vector rotated, and multiply it by the linear acceleration, and this will start to increment the linear velocity by this vector that we are creating here. And as I said, we have to make up for the delta time by multiplying it by delta. Actually, I have to make a small correction here, because vector2.right is what we are going to do to move the spaceship, but this is what we are going to use in this calculation here to tell if it is moving or not. So I'm going to use the thrust direction here instead of vector2.right, but turning from toggling from vector 0 to vector 2.right is how we are going to tell the spaceship to move or to stop. So this is the proper equation here. And then we have the angular velocity that follows a similar approach. We have the angular velocity, and we are going to add it up by the angular velocity, the turn direction times the angular acceleration times delta. And believe it or not, this is everything that we need to do in the spaceship. Now we are going to create two methods to actually make it start and stop. Remember, as I said, the way that we make it start moving is by toggling its thrust direction from vector 2.0 to vector 2.right. And I don't want other classes to understand this. I just want them to tell the spaceship move or stop. So we are going to create an interface here, and we are going to encapsulate this toggling of the turn direction into two methods. The first one is move, and this is the contract that we are creating here. So other classes don't have to pass anything to this method in order to make it work, but they will also not expect anything from this method. So what this method will make is turn the turn direction to vector 2.right, and the second method, which is the stop method, will do the opposite. It will change the thrust direction to vector 2.0. And these are the methods that we are going to use in the controller to make the spaceship move or stop. Now we are going to do the same, but for the turn direction. We are going to create an interface for the turn direction. And for that, we are going to make a contract that will ask for a direction, which will be an integer and will not return anything. So every class that tries to use the spaceship class will have to fulfill and agree to fulfill this contract. They will have to pass a direction that will be an integer, and they cannot expect anything from this method. And what this will do is to set the turn direction to wherever direction that we received, and it will actually clamp this direction between -1, 0, and 1. So what this does is basically, sorry, what I should do here is pass the direction, if I'm not mistaken. Yeah, the minimum, which is -1 and 1. And this should be an integer. Well, what this will do is to prevent that values that go below -1 will be used for this calculation, because this will make so that the spaceship will turn like crazy. And the same thing for values that go beyond 1, but values that are between this will be taken into account and will be properly taken in this calculation. But we need to turn them into integers, because Otherwise, we may have something that is very slow, and this won't work. But, well, this is the spaceship class that we are going to use to control our spaceship. And if you want to see if this is already working, I'm going to add a sprite just for the sake of visualization. We are going to take out this sprite as soon as we finish this test. So as I said, an image is a data that we work with, that we process in our games. So this is the image that we have, and a sprite is nothing but a class, a node specialized into processing images, in processing textures, because a texture in Godot engine is different from an image. We have an image and we have a texture. Just like I said, if you can turn everything into objects that we can actually control. So Godot engine could just work with a PNG image, but then we wouldn't have the methods that they allow us to use by encapsulating an image into a texture class. So this is what we call wrapping. Godot engine took a common image and wrapped it inside a class that they call texture, because this allowed them to process the data from the image way better. And in this case, we are going to enable the region, and we're going to edit this region, and you can see that we have many data here. So I'm pointing out these things to you because this is interesting to understand. We are working with data, we are mutating data. So we are mutating whatever region that the sprite should display, and instead of displaying the whole image, we are saying, hey, cut off the image into small pieces using this out slice. And I just want to show this piece right here. So let me just show you what happens when you don't take into account that Godot engine rotation default is a vector pointing to the right. As you can see, the spaceship is pointing upward, and this is a vector that has a 90 negative degrees rotation. So I will have to offset this by 90 degrees like this to make the spaceship move pointing, to make this whole calculation be displayed correctly. So I'm going to save that. I'm going to position this right here, and I'm going to, in the ready callback, I'm going to tell the spaceship to move, just so we can see it moving around and see if everything is working. Oh, as you notice, this is sorry, I closed the project by mistake. But as you saw, the spaceship started to fall, right? This is because we didn't set the spaceship taking into account what a spaceship will be used for. Because the physics body here, the rigid body, will simulate physics, right? And by default, it has a mass and a gravity scale, because it takes into account that it will fall. But since we are working with a spaceship, the spaceship won't fall. So we are going to toggle off the gravity scale by turning it into 0. And well, I will add some virtual mass to this spaceship because I wanted to react to collisions as well in the future. So I'm going to set this to 100. But even though this is set to 100, since we don't have any gravity scale, we can play a little bit with that. So as you can see, it is accelerating and accelerating ever faster, and this is because we didn't set the damping. So damping is the amount of energy, of movement, of energy that the body loses along time. So I figure out that for this purpose, a damping of 3 in the linear velocity and a damping of 1 in the angular velocity is enough for it to maintain a constant speed, which is exactly what we want. So yeah, the spaceship is already working, and the next thing that we are going to do is the controller, so that we can control this spaceship. So I'm going to remove this sprite because I don't want every spaceship to look the same, and I'm going to remove this move here because this is not what I want. I don't want every spaceship to just start moving out of nowhere. And now we can move on to the keyboard part, to the controller part. The next thing that we are going to create is the spaceship controller. And why don't I add this inside the spaceship logic or inside the player logic? It's simply because the spaceship controller is a very specific problem that I want to solve. I don't want to be a general solution for every type of controller, for every type of movement on other projects. I just want this to control a spaceship. And by scoping this down to control a spaceship, it will allow me to reason better about how I can solve this issue. And for that, I'm going to create a new scene here and add a simple node, because a node will provide us with some methods that we can use to process this logic that we are process this problem that we are trying to solve, namely the unhandled input method. And well, I'm going to call it spaceship controller. I'm going to save it in the actors because this will be something exclusive to the player. So I'm going to create a player here, spaceship controller. I'm going to change the way that Godot name my stuff, spaceship controller. Let me just change that because I find this to be very annoying. So project settings, naming, and editor naming, Pascal case, scene naming, Pascal case as well. So close. And I'm going to create the script, save. And what we are going to do here is to ask for a spaceship. So I'm going to export a variable that will be the spaceship. And this is the thing. So remember that we are creating a vocabulary. Now that I can give a name to a variable, I can call this a spaceship, I can call it whatever I want. But now I can say that it will be a spaceship. It is from the spaceship type. And this will allow this spaceship controller class to have more context about what we are working with. Okay, so the core mistake here is that I didn't give the spaceship class a name. So let's say class name spaceship, and this should fix that error. And there we have it. So now we can say that the variable spaceship is of spaceship type, and this will allow us to set the spaceship in the inspector as well, using the export, using the inspector to set the variable. And it will filter every other node, and it will only allow this variable to be set to a spaceship type node. And what we are going to use here is to export variable that will be the trust action, actually, which will be by default trust action. Why am I doing that? Because if I want to reuse this on another project, I can change the action that I want to use for the keyboard. So the action is whatever we set here in project settings, input map. These are the actions. So it's actually just trust, right? So trust, turn right, turn left. This is what we're going to use here. So trust, export variable turn left, I'm going to duplicate it, turn right, and turn right. So this is everything that we need in order to accomplish the logic that we want. I'm going to basically just copy and paste the logic so we don't waste time with that. But what I want you to understand is that we're going to use a virtual method called unhandled input that instead of providing a delta time like the physics process provided to us, it will provide an event. An event is a variable of class input event, and it will allow us to understand what is the event, the input event that just happened. Is a key pressed? Is a key released? Is a movement of the mouse or anything like that? So I'm going to skip right to the point where this is already implemented here because I don't want to waste your time with some implementation details. So here I am with the logic already implemented. So as you can see, it's a very simple logic. So we have a check to see if this event is an echo. An echo is basically a repeated event from something. So for instance, let's say if you press the key and hold it pressed, it will keep emitting that the key is pressed. We don't want to listen to that. We don't want to treat this kind of event. So this is what what we call a filter. We check a condition and we use a return. We didn't talk about return because this is not exclusive to object-oriented programming, but a return is basically something that you use to make the function return from this point, and you can return a value. So if this is not a void function, it will have to pass something in return. But when you use return like this, it will basically stop the processing of this function right here and will go back. So in this case, if this is an event that is an echo, we don't want to deal with that. It doesn't enter in our logic. It doesn't interest us. So we are going to move back to the logic. So but if it's not an echo, we want to treat it. So we are going to see if this is the trust action pressed. If this is the trust action pressed, we are going to tell the spaceship to move. If it is the trust action released, we want to tell the spaceship to stop. If this is an action pressed telling the spaceship to the right direction, the right key, it will tell the spaceship to turn to the right. If this is the left key, it will tell the spaceship to turn to the left. And if this is something that is a little bit advanced, but this is a singleton. We are going to talk about singletons in future videos. But I'm checking here if the turn left and the turn right actions are not pressed. Both of them are released. If this is the case, I want to tell the spaceship to stop turning around. So this is basically the spaceship controller. It takes some input events and it checks if they are relevant for us. If they are, we tell the spaceship to do some procedures accordingly and pass some data to it as well. So this is basically what the spaceship controller is. So we already fulfilled the spaceship, which is a rigid body, an object that moves with physics simulation movement. And we also just fulfilled the requirement of having an object that controls a spaceship. So now we can create the player. So I'm going to create a new scene here, and for the player I just want to use a node 2D, a default node 2D, because I just want to position the player in the game world, but after that I want to move using the spaceship. So there is no reason for the player to be a spaceship. The player has a spaceship, but the player isn't a spaceship. This is important to understand because the player will bundle a lot of other things that are not related to the spaceship. Namely, for instance, the health resource, the energy resource, so on and so forth. So it's important to abstract the player not as being a spaceship, but as having a spaceship. Okay? So that said, I'm going to call this player. Going to save it inside the actors player folder, player, and well, now we just need to compose the scene with what we created. So I'm going to add a spaceship here, a spaceship controller, and in the spaceship controller I want to assign the spaceship as being this very spaceship that we have here. So now we can control this spaceship. You can see that we have a warning here. It's because we don't have a collision shape yet. I like to leave this as it is until I make a concrete implementation of the rigid body that I'm using. So in this case, I'm going to add first the sprite, because now that I have a player, I already have in mind what the player looks like. I want to give it a graphic, so in this case it will be the spaceship that we used in the previous test. So I'm going to add a sprite here, use this texture, region enabled, edit region, auto slice, and I'm going to select this. I'm going to rotate it so that it makes up for this. This is a mistake that I made when I was drawing. I always draw pointing upwards, but I should start making it these spaceships pointing to the right. This was a mistake of mine, but I'm going to add now the spaceship, the collision shape for the spaceship, just so we have something to work with. New circle shape, and it will enclose the whole sprite here. So if I save and test this, probably it will already be working. So there we have it. We have our spaceship. I think that I will increase its movement speed. So I'm going to close that. And I think that I'm going to embed it. So in the spaceship, remember that this is a value that we use in the class, but we talked about serialization. I'm going to serialize a new value here, which is 600, probably 800. And Godot will use this serialized value instead of the default value in the class, okay? So I'm going to play it, and there we have it. Cool. So we are done. We finished up with our task for this video. Well, for this video, that was it. I know this was a long video, but I hope that it was valuable to you, because I really want to help you make great games. And for that, you need to understand the basics of object-oriented programming, because this will allow you to think better and to solve better and more complex problems. Well, that said, if you want more help, if you want specialized help with your games, and if you want to learn everything from the basics of programming to releasing your game, the link will be in the description for the mentorship, the mission XVIII, where you can enroll for $500. If you are a Ludonaut, you have 20% discount, so the link will be in the description for becoming a Ludonaut as well. By becoming a Ludonaut, you enter in the community as well, and you can ask questions, and I will help you with your questions using the Discord server. But for this video, that's it. I hope you enjoy it. Thank you so much for watching. Keep developing, and until the next one. Bye bye.